Or, sorry, question number 34, part A. If n denotes the natural numbers and a relation set of natural numbers and R is the relation that is defined from on n cross n, and relation says that the ordered pairs AB is in relation with ordered pair CD if A into D uh, into B plus C is equal to B into C into A plus D. So this relation is defined for the natural numbers to natural numbers. So this is the natural number. This is the codomain. So n to n, the relation is defined, and we have the ordered pairs here, A, B, and C, D. Now they are in relation if A into D, that is A into D, and whatever is left, add them, the other elements, is equal to B into C into A plus D. So then we can say that A, B is in relation with C, comma D. Now let's check it for the equivalence relation. For that, let's check the reflexive, whether it's reflexive or not. So for reflexive, we have to check whether A, comma A is in relation with itself or not. So I'm going to check the relation of A, comma with A, comma B. So for that, I have to multiply A with B and add A plus B, the and then B into A, which is AB, and then A plus B. So AB, obviously these two sides are equal. That means A comma B is in relation with A comma B. That means this relation R is reflexive. So R is reflexive. Now let's check it for symmetric. And to check it for symmetric, let's say A comma B is in relation with C comma D. So this implies that AD into B plus C should be equal to BC into A plus D. Now, if this is equal, I can change the order or change the sides. BC into A plus D is equal to AD into B plus C. So that means C comma D is in relation with A comma B. So that means R is symmetric. Okay, now let's check it for transitive. And to check it for transitive, let's consider uh, two ordered pairs, or the set of two ordered pairs to be in the relation. Now let's say A comma B is in relation with C comma D. Let's say A comma B is in relation with C comma D, and this is D. So C comma D is further in relation with let's say E comma F. So if we are able to prove that A comma B and E and F are also in relation, then this is transitive. So this is in relation means that A into D plus B into C is equal to BC into A plus D. And next one is C into F in plus E into D. C into F plus E into D is equal to D into E into C plus F. This is what we get from these two relations. So A into D plus B plus C is equal to B into C into A plus D. Okay, from this one, if I use this, I can write it as B plus C upon BC is equal to A plus D upon AD. And which gives me, if I separate them, so B upon B plus C, C upon BC is equal to A upon AD plus D upon AD. This gets cancelled. And finally, I have 1 upon C plus 1 upon B is equal to 1 upon D plus 1 upon A. Okay. Okay, next one is, if I use this one, I can write it as E plus D upon DE is equal to C plus f upon cf. So this becomes 1 by d plus, this is 1 by d plus 1 by e is equal to 1 by f plus 1 by c. So I have these two, 1 by c plus 1 by b is equal to this. Okay, now I am going to add these two results. So let this be equation 1, this be equation 2. So I'm going to add these two. So adding these two will give me uh, so 1 by c plus 1 by b plus 1 by d plus 1 by e is equal to 1 by d plus 1 by a plus 1 by f plus 1 by c. Okay. Now, for these two, can cancel these two. This gets cancelled and this gets cancelled. So finally, I have 1 upon b plus 1 upon e is equal to 1 upon a plus 1 upon f. And if I take LCM for these, so this is LCM BE, so this is E plus B is equal to LCM AF, F plus A. And I can write it as, so this becomes, let's cross multiply this, so A into F into B plus E is equal to BE into A plus F. Okay, if this is the result, then according to this, A into B is in relation with E into F. So that means R is transitive. So R is transitive. Now R is transitive, R is symmetric, and R is reflexive. So that means R is equivalence relation.